Okay, greetings YouTubers. So this is going to be the most difficult part of the tuning process for me to explain. And that is how we do our load scaling for boost so that we can adjust our timing up into those, boosted higher load cells, which we don't currently have in the tune. And the reason this is so hard to explain is because when we're working with these Foxbodies and these EEC-IVs, we're essentially trying to make decisions based on the amount of boost we're running at any given point, but there's no actual measurement of boost in this computer. There's nothing we can directly log without additional hardware and whatnot. So there's a lot of challenges with doing this, and this is where we're going to get into a lot of math today and a lot of work in Excel, actually. So the central challenge is this: we have to first decide how we want to scale this table. So this is still with stock scaling for the load right now. We've already handled RPM in the last video, so we're now in the 5,000 and 6,000 RPM range, but we have to decide how much higher above 75 do we even want to go, and what are we willing to sacrifice in the mid-range to do that. And then of course later in this video we also then have to fill in all the values of whatever our table ends up looking like and try to do it in a way that's not going to blow anything up. Okay. So based on this, I've actually been working this morning on a big spreadsheet, and we're going to kind of work our way down the sheet one thing at a time. And really what I want you to pay attention to is this. We're trying to ultimately simulate a stock computer setup as a starting point and adjust from there. What do we have from the stock tune that we can work from? Well, we have the current Sealevel spark table, and this is just straight from an A9L, no changes. There is, by default in the factory, there's a wide open throttle spark table that's very simple and based only on RPMs. We're not going to use that, but it can be used for now as a point of reference, even though it's turned off in the tune. And we've also, if you remember in the video around configuring fuel, we had hopefully run some kind of a test where we've run the car naturally aspirated with at least good enough tune to not blow anything up. And we've run it all the way through the RPM range and measured what was the peak load we achieved at various RPM points. And we plotted those here to assist with fueling. But this is also going to help us a lot today in determining what to do with spark. So really all the decisions we're making are going to be based on those three tables, and everything else in this spreadsheet you see that's zeroed out right now or empty. This is all the stuff that ultimately we're going to fill in. And by the time we're done with that, we will end up with a final spark table, and this will essentially run everything but idle off of the one table. Okay, so the first thing I want to talk about here, this isn't really just related to spark, and we've sort of maybe mentioned it in other videos, but this is a concept called interpolation, and you need to be very clear on what that means in order to make the decisions and understand the rest of what we're going to do today. So interpolation is this simple. If I look at any one of these things in the tune that has a table, and all I have is a value in this cell, and I have a value in a neighboring cell, either above it, below it, left, or right. And interpolation is basically saying that anytime the car is operating between the lines, because you're never going to be just sitting all the time at exactly 2,000 or exactly 2,500 is in this case, but you're somewhere in between. So what the computer's job is to do is calculate as quickly as it can, well, what is the exact RPM? And if we draw a flat line, thinking about like plotting this on a chart, if we draw a flat line between this value and this value, we could then sort of understand what the actual value would be at anything in between two given values. So that's the idea of interpolation, is it's constantly making those calculations. And when you have linear interpolation, that's exactly what linear means. We're on a plot. If you plot this stuff out on a chart, you'd be able to draw a straight line between any two points. Any two neighboring points. There's other more fancy calculations and some newer computer stuff, but it's computationally a lot more expensive to do that stuff when you're dealing with logarithmic curves and stuff that's even more complicated than that. So, these old computers, everything's always linear. And, honestly, even a lot of the newer stuff too is still linear because in a lot of cases, there's enough data points to work with where it's not really a problem, and the things happen so fast in real time that maybe not an issue. Okay, so that's the concept of interpolation. So the very first challenge for us today is to fill in this table where we're essentially trying to start with the stock Sealevel table, and we want to adjust some things so that we're also factoring in, well, what would the computer have done with this wide open throttle table had we still left that turned on? So we're essentially trying to find a technique that blends the two of these. And you could eyeball this, and this is actually a pretty simple thing to do, and it would be pretty close. But I want to show you mathematically how to do it the correct way that is exact, or as precise as we can get. So first thing I can do is I can plug in some of these numbers already. So what we know is that, again, we've sort of cut out the bottom two columns in the last video. So you can see our new table is going to start at 900, but we generally kept all of these the same up to 4,000, and then we added 5 and 6 on top. So the first thing we can do is we can start down here at 5 load and 900 RPMs. And I want to copy this. Actually, we'll just go ahead for now and copy all the way up to the top. So we'll grab that part of our table. We'll throw that in here. And then, you know, with any table in these computers, I've mentioned it before, I'll mention it again. If you're doing something that operates outside the bounds of the highest column or row in a table, then it basically just freezes that value. So as an example, if I stayed at 75 load, but I exceeded 4,000 RPMs and kept going to 5 and 6 and 7,000, but I was still at 75 load, this value would sort of carry over as though there were additional columns. It won't go any higher or lower. It'll just kind of stay the same at that point. So what that means is that because we didn't have in the original tune anything higher than 4,000, that means essentially all of these values continue to apply, and I can just copy those here. Okay, so that's the first thing we can do, but now we need to merge in some of this data. So the first thing we have to do is we have to create a little calculator here, and this is going to be very quick, but we're going to use this a couple times. And what the calculator's job is to do is, if I want to know, for example, if I want to know the value at wide open throttle at 4,000 RPMs, according to this stock table, well, we don't have a value at 4,000 RPMs. We have something a little higher than that, which is 5,000. Got something a little lower at 3,500, but there is no 4,000. And I know what the values are at these two places. So again, using that concept of linear interpolation, what we can do is build a calculator where we can plug in any number between the two that we want, and it will tell us the exact amount of spark or whatever the other value is that we're looking for. And then we can start plotting in and filling the blanks. So here's what I'm going to do. So I'm going to start by, and again, this is what we're trying to fill out, is this guy right here. I'm trying to make the equivalent wide open throttle chart just like this one, but using the RPMs that we have available on our configuration. So all of these numbers right here, this matches our new RPM scaling. And the only thing that we know from this factory spark table is there was a value at 5,000. That's one of my numbers. So I've already put in 26 degrees there, but the rest of these numbers are somewhere in between the ones that the factory tune had. So the first one I need to figure out is 6,000. So here's what we're going to do. If I look on here, I don't have a 6,000, but I have the next number higher and the next number lower. So I'm going to plug those two in here. So in this case, it's 16,383. And the one that's lower than that would be 5,000. So those are two known things. I'm going to have to decide what I want in the middle. So we're trying to find 6,000. That's going to be our unknown. So I'll go ahead and plug that number in there. So next closest that is known, higher and lower. And then what were the stock values that we do know at those RPMs? So here, that was at 26 degrees timing. And at 5,000, it's actually still 26. So you actually don't even really need to run math here. The value is still going to be 26. It didn't change, so you're still flatline 26. So I'm just actually going to throw that one in for now. Okay, 4,000. This was the first time we can actually use the math. So we need to do the formula here. So 4,000 is between these two. The value is not the same, so there is going to be some change here. So let's now plug in those numbers. So if we're looking for 4,000, 5,000 is the next one up. 4,000 is what we're looking for. 3,500 is the next known value below. It is 26 degrees up here. This is what we have to figure out. And the low was 22 degrees. Okay. So here's how we're going to do this formula. So the first thing we want to know is, going from this RPM to this RPM, what's the total change? How much did the timing increase going from here to here? Now we can just look at it and know that it's 4, but I'm trying to make a calculator here that's dynamic, so we're going to do a formula. So this essentially equals this higher value minus this lower value. Okay, that gets us to 4 degrees. So that tells us how much did it change during the course of going from 3,500 to 5,000. Now what we want to do is this, if we change a total of 4 degrees over that many, over 1,500 RPMs, then what we're really trying to say is for every 1 RPM that we went up, how many degrees did we go? It's going to be a tiny fraction of a degree of timing, but that's what we're going to do. So now what we want to do is we want to take that 4 degrees and we want to divide that by the amount of RPMs that went up in that full range, which is 5,000, our high number, minus 3,500, our low number. Okay. So now what this big decimal represents is for every 1 RPM we went up from 3,500 all the way to 5,000, if you're just following a linear path, we went up this much, this number of degrees of timing for every 1 RPM. Now, the final thing is to figure out, well, what is it at 4,000? We need to understand, well, okay, if that's per RPM, well, how many RPMs are we increasing going from the low to the one we're trying to figure out, which in this case is 500. And we want to multiply the current value we have here by 500. And that should tell us a total of how many degrees would we have to increase from here to here. So what we can do now is we take this entire number that we have and we multiply that by, again, this number minus this number. So we're multiplying in this case by 500, and now we have 1.33 degrees. So now what we know is that to figure out what timing we have at this unknown middle RPM, we need to go this many degrees above what we had here. So the final thing we do now is take this 1.333 and add it to that value, and that will give us the timing number that we have here. So the last thing we need to do is, let's see, that would be cell C17. So this equals C17 plus this entire range of stuff here, and we end up at 23.33 degrees. Now, before I just go plugging that number in here for 4,000, which is technically the right number, you also have to understand that when you're dealing with these timing tables in this strategy, it will only let you plug in numbers in increments of 1/4 of a degree. So I can't have a 23.33, but if I rounded that to the nearest quarter, I would have 23.25. Excel has a function to do that also. It's called mround. So basically, if I take this entire formula and I start it with mround, put that whole section inside of parentheses and add a comma here, then what I can say is I'm rounding it to the nearest what, and I can put in whatever amount I want. So if I'm trying to round it to the nearest, basically 0.25, I can put a 0.25 in there. It'll automatically round my number, and we have 23.25. Okay, I know that's a lot of math, and we're going to have even more complicated math, but this is now a very good calculator. So at this point, for anything else we want to calculate, we can put in these 3 values, this value, and this value, and it'll tell us what this is going to be for anything else we want to know. Okay, so there's our 23.25. Okay, next thing I need to know is 3,000. I don't have a 3,000 on this chart. Next one up is 35. So I'm going to throw 3,500 there. 3,000 is what I want to know, and 2,600 is the next one below it. At 3,500, we are at 22 degrees. And at 2,600, we're at 22.5 degrees. So this is telling us that the closest in between is 22.25. Okay, moving down, 2,500, that's between 26 and 2150. So we plug those numbers in. 2,600, I want to know 2,500, and we have a 2,000. 2,600, we're at 22.5. And at 2,000, I'm sorry, actually we have 2150 down here. So at 2150, we are at 21.5 degrees. So that also gives us a 22.25. Okay, next is 2,000. We have a 2150 and an 1,800. Okay, and at 2150, we're at 21.5 degrees, and at 1,800, we're at 18.5 degrees. So 2,000, we're at 20.25. Okay, bear with me, guys. We're getting close. Okay, next one, we have 1,800. We want 1,500, and we have a 1,000. At 1,800, we're at 18.5 degrees. At 1,000, we're at 8 degrees. So at 1,500, we are at 14.5. Okay, now this is going to get easy right here because the next two values we need, 1300 and 1100, are still in these ranges. So the only thing I have to change is that number. And we have 12 here, and at 1100, oops, we have 9.25. Okay, and then at 900, we'll have to do 1000 here, 900 here, 0 here. At 1000, we are at 8 degrees. At 0, we are still at 8 degrees. Therefore, at 9, we are at 8 degrees. Okay, so that's a lot of stuff to go over. But now what we have is we've essentially created a new version, a new flavor of the wide open throttle spark table, but one that uses our exact points and that we're going to use for our sea level table. Okay, so that was a pretty good exercise to go through. So now what we need to do is we need to modify some of these top numbers in here to reflect these values. And I just want to kind of review something here. So going back into binary editor for a minute, when we go up into this air and go to load, just in case you didn't watch the other videos, this table right here is one that basically you should have tried to plot the maximum load that you were able to achieve during wide open throttle, naturally aspirated. So again, if you're like running a blower, and that's kind of the basis of this video, you take the belt off and go run the car. Again, it assumes that the rest of the tune is healthy enough to do that. But if it is, you take the belt off, run the engine, figure out where did you sort of peak out load, make sure you create a point at approximately that RPM. So in our case, that point was right here at about 4464, and you expect load to be basically less both before and after that point. And this is generally going to be where you achieved maximum torque and maximum power. Okay, so we have these numbers. We've already plotted this, so I'm working off of these numbers. Here's the stock ones, but we're going to work from these guys here. Okay, so because I plotted this, the reason I'm bringing this up, and I've just copied those values here, we want to just consider the fact that at wide open throttle, we know where our load is. So if the highest row in a stock setting is 75 load, well, we already know that at all three of these, we're definitely well above that at maximum potential, which would be wide open throttle. So we should feel very comfortable just plugging these numbers in. So for anything from, probably about 3,000 RPMs to 5,000 RPMs, we're definitely above that. So what I'm going to do is go into my 75, and for these three values here, I'm going to plug in our numbers that we just calculated. So at 3,000, we decided we were at 22.25. At 4,000, we're at 23.25. And at 5,000, we're at 26. And then the computer, we also know that it's going to stay locked at 26 above that because that was the highest value it had in the stock table, and it'll just keep that however high you go above that. Okay, so those are all at 26. Now, going back down to 2,500, the thing is we're probably getting somewhat close to that, so we could probably go ahead and plug in our number also there, 22.25. And then when we get down here, we questionably start to get closer into these values here, but this is probably a pretty good start, is leaving this stuff this way. And so I'm going to go ahead and even though the maximum load we can achieve at some of these really low RPMs is considerably lower, I'm still going to go ahead and plug in the numbers that we had here. This will make a little bit more sense later why this is okay. Okay, so we've got 8 there. We decided 9.25 here. And we decided 12 here, 14.5, and 20.25. Okay. So that's all of that. And, basically what you should pretty much always have in a smooth table is as the load is going up in a given column, the value should keep going down or stay the same. So like right here and here, we have a problem. We go from 18 all the way down to 11 and then back up. That's kind of an odd curve. So if nothing else, I would recommend you make this the same as a lower value and bring that up here. Same thing here, 14.5. And then we kind of have the same issue here. And this makes sense that we're having this issue because, again, this sea level table originally had much lower values up top, so it would follow our smooth curve that we're describing, but it wasn't trying to account for two different styles of driving in one table, which we are now. So we really probably ought to do some kind of averaging here for all of these guys up here. And a pretty simple thing we can do, we could either use our calculator here, or we could just run the math and throw in an average ourselves. We got the calculator, might as well use it. So if I've got at 5,000 here, 26 and 27, and I want to find the middle ground, you know, we could use the calculator and do that. But I don't know, I'm feeling lazy. Let's just type it in. So let's run 26.5, 26.5. Here, let's run 25. This will be close enough because we're going to do a bunch more massive changing here in a minute anyways. We'll go with about 24, 24, 23, and might as well keep smoothing this stuff out. We'll go to about 17, 15, and let's go to 12 and 12. That ought to be close enough for what we're trying to do. Okay, so we still haven't solved the final problem we're trying to get to, which again is going way above 75 load, but we've essentially gone through enough effort to merge these two tables into one so that we can continue to leave this table shut down in the tune. And now we just have to figure out how to get things to scale up from here. So now that we've done that, I am going to do one more thing, is go back into my RPM area, or I'm sorry, my Spark area. And I want to turn off this wide open throttle table. I turned it back on temporarily just so I could get back to these numbers. But man, you're going to blow shit up if you don't turn this back off and you forget. So I would recommend you double check now. We shouldn't ever need to look at that table again. That needs to go bye-bye. Okay. So that's gone. And now you can't even see the wide open throttle table. Okay. So now we are absolutely running back on just the Sealevel table again, but we've sort of created this new conceptual kind of same thing here. Okay. Now, the next question we have to ask ourselves is, well, how much higher do we actually need to go with our load? Because again, we only have this many rows to work with, and that's not going to change. So there's a very delicate balance here, and we don't want to, you know, just get crazy here and lose all of our drivability by killing too many of these. So we really need to think this through. Now, the first part of that, though, is knowing, well, what's the highest number I need to achieve? And there's a way to estimate it. This is not perfect, but it is an estimation. Now, if you think about when you go buy any supercharger kit or turbo kit or whatever that you throw on these Foxbodies, it's at least rated or tells you, hey, if you use this pulley or this wastegate spring or whatever it might be, you should be at this many total pounds of boost. And if you're running something like a turbo, generally what that means is, you know, you're going to have a little bit of lag when you step on it, depending on the turbo. It'll spool up and get to that boost. And then once you sort of get into that maximum boost, if the wastegate's doing its job and everything's holding, that amount of boost should stay pretty flat throughout the range, all the way through. With a blower, at least with a centrifugal blower, which is probably what you're going to end up with on a Foxbody, with a small block Ford in most cases, it's more of a linear curve. You know, you don't hit instant boost immediately. It really needs RPMs, and as the RPMs climb, the boost climbs, and it's relatively a flat curve in most cases. So what we need to do is take sort of a manufacturer's spec of, hey, you should get with this pulley 8 pounds or 10 pounds or 12 pounds. And we need to sort of come up with a map where we can estimate approximately how much boost we have at various RPMs. And again, for this exercise, because turbos are a lot easier to figure out, you just need to know when the boost hits. We're going to focus on a blower car, like something like a Vortec, just a real simple combo. Okay, so what we're going to do is we're trying to fill in this table to figure out what is approximately the maximum amount of boost that we have. And the reason we're trying to even get to this, by the way, is that, you know, tuners for years have had some kind of baseline standards. If you know what your engine can safely do naturally aspirated as far as timing, then people say stuff like, well, from that, if you pull 1 degree for every pound of boost you run, probably still pretty safe. And in my experience, and this is pump gas, by the way, if you're running ethanol or race gas or something, then don't think that makes any sense. But standard, just street car, pump gas combo, that's a pretty good rule. I've never blown anything up. That's a pretty safe start. Now, other people will argue that once you really want to get things dialed in, probably at the couple pound boost range, you don't need to start pulling timing right away. Probably some truth to that because the cylinder pressure is not that high. The temps aren't that high yet. But anyways, we're going to kind of work off of a basic understanding of pull a degree for every pound of boost, and that's our goal. But we need to figure out how much boost we have. And because we don't get to plug these numbers in based on boost, we have to plug them in based on load. Then we need to take the boost that we think we're going to get and then figure out what the load is going to be. And then we can start to scale this table in a way that makes sense. So, using a lot of words here, I apologize, guys. So now what we have to do is we have to take, again, we've already done this mapping where we figured out, well, what is the maximum load we've achieved at various RPMs, but these RPMs are not the RPMs we work with in this table. So what we have to do now is using the same type of calculation of inferring sort of the linear interpolation of this amount of load at these things in between the numbers. That's what we're going to do to fill out this table right here. So this 6,000 through 900, again, I've already plugged in what we've decided on for our RPMs here. And the only number that we actually had an exact estimated load was at 6,000. We've got to fill the rest of these in. So I'm just going to reuse the same calculator here and fill in the blanks. So if I need to get 5,000, we have the one above it is 6,000. The one we're trying to create is 5,000, and the next lowest down is 4,850. At 6,000, the value is 71.5, and at 4,850, it's at 82. So that tells us at 5,000, we're at about 80.75 load. Okay, next one, 4,000. So 4,000 is going to be between these two guys. So we have a 4464. We're looking for 4,000. And we have a 3,500. This is at 80.5. 4464 is at 84. So 4,000 gives us 82.25. Okay. Next one, 3,000. So 3,000 is between these two. So we have 3,500, 3,000, and 1,000. At 3,500, it's 80.5 degrees, and at 1,000, it's 67.5, not degrees, I'm sorry, load. This is what happens when you use the same calculators for multiple things. Okay, we got 78 there. So same thing as before. Now we're going to have a whole bunch of stuff that stays within that range of 3,500 to 1,000. So really, we can get all these numbers very, very quickly just by changing. So 75.25, 72.75, 70, 69, number, and 68. All right, and then the last one, we have to change these. So 1,000 here, 0 here, 65 here, and 67.5. And that needs to be 900. That gets us to 67.25. Okay, so same calculator, just kind of a different use, load instead of spark. But now we have a detailed map of, pretty close estimate of load at the exact RPMs that we're measuring in our spark table. So this was important. Now, this next column, this actually doesn't technically matter for what we're doing to tune. I just want to give you guys kind of my thought process here, be it perfect or not. So the concept is that generally speaking, other factors, this isn't exact, but it's, again, these are just estimates. If you take a naturally aspirated car and you've dynoed it and you have your whole power curve, and then you double the power for having 1 bar of boost pressure, which is about 14.5 pounds of boost. So 14.5 pounds of boost should have about double the power. Well, to have about double the power, you'd have to have about double the airflow. And of course, all the fuel to support that. And because load in these computers is directly related to airflow coming through your mass air meter versus the cubic inches of your motor, what that means is if you're doubling airflow, you're probably doubling load. So theoretically, this is all close, not exact, but if you want to figure out what load you're at 14.5 pounds of boost, 1 bar, you could just double all these numbers. It ought to be somewhat close. So I'm just going to say this equals the cell next to it times 2. And again, this is just a point of reference. This doesn't actually matter for anything that we're doing in the tune, but I just want to show you something here. because this is at least understandable. So if you know this is 14.5 pounds of boost, you should have a pretty good idea of how much boost you're trying to run in your combo. I don't know what that is, but you should kind of know what your pulley is and what people will at least sort of generally tell you'll get. Not every combo is the same. Just because it has a X inch pulley doesn't mean you get Y amount of boost, but you should have some idea. You shouldn't be too far off. Okay, so just looking at this here, I can tell you most of you guys running just simple combos with little smaller bolt-on blowers, nothing crazy, just the normal stuff. You're probably not even running 14 pounds boost. You might be, but a lot of those smaller blowers are going to start kind of running out of steam somewhere between 12 and 18. There's, of course, blowers that can go way past that, and turbos will definitely go way past that with almost any of them. But with the blower car, you're probably not even getting this high. So the reason I'm bringing this up is because these are all based on some actual measurements that we've done from data logging. And this is where you're at 14.5 pounds. You have to ask yourself, the biggest number in here is 164. Is there any way in hell you're even planning to come close to that amount of boost? And if you know, like, man, I'm just running the baseline 6-pound Vortec kit, maybe it gives me 7 or 8, but it's not going to be anywhere near 14. There's just no way. Then you already know these numbers are really, really high. And you probably don't need to scale your table all the way up to like 200. 200 is the max we can scale here when we're setting this up. And it's important that we don't exceed it. And that'll be a whole topic for another discussion. But most of you guys won't hit that with these simple combos. And of course, these are based on my NA load numbers. Yours might be different. If they're substantially higher, well, then these are going to be substantially higher too. But all these calculations will handle that for you. Okay, so what I'm going to do here is this is just kind of me BSing my way through it and just throwing some numbers out there. But let's say you've got a Vortec combo and, you're trying to pull it out a little bit and you do some research online. People tell you, man, that ought to be good for, 11 or 12 pounds of boost. That's a pretty reasonable thing a lot of guys would go do. And because it's a Vortec and centrifugal, that that's really what you're going to achieve in the higher RPMs, and it'll be lower down low. So I'm just going to put in some estimated boost numbers here. Now, later on, if you can at least get your tune relatively safe with the blower, finish all this and start logging. And I know you can't log the boost without some extra equipment, but what you could at least do, if nothing else, is do a data log with what you can log, throw a camera on your boost gauge in the car, and just go back and watch it. And you ought to be able to figure out pretty quick if that camera can show you your tack and your boost gauge in the same view. I mean, you can get at a much more accurate estimate here. But regardless, here's what we're going to do. So I'm going to go in here and say that, let's say we're running like 12 pounds up here. And some of these blowers actually tend to sort of lean over a little bit. Like, it doesn't just infinitely keep pushing out more boost. If they start running out of steam, you might see a hair less boost up here. So let's say we do something like 12 here at 5,000, maybe 11 here. Maybe at 4,000, we're running, maybe 8 pounds of boost. Down here at 3, maybe we're running, 4 pounds of boost. And at 2,500, we're really just getting started. And let's say down here, 1 pound and 0 the rest of the way. I mean, the truth is you could theoretically get boost out of it, maybe even at these lower RPMs, but do not beat the hell out of your car at 1,500 RPMs. That is not a good idea. Your ringlands will thank you if you don't do that. So really, honestly, racing, you should never be just beating on it unless you're at about 3,000 RPMs or higher. There's some benefit to doing some logging and dynoing for drivability. If you have to lean into it, somewhere around 2 to 2,500, but it's not something you want to just repeatedly do. There's no reason you should be down there during racing other than just getting off the line. Okay, so I'm just going to throw these numbers out here for the hell of it. These you'll have to maybe adjust or put in once you can get some more accurate logs, but it's a ballpark. That's all this is for, just ballpark. Okay, now your estimated load now, this is the important thing we're actually trying to figure out is if this is what you did NA and you think you know how much boost you're going to get, and these are your estimates, then what's my load at each RPM? Because guess what? You measure by load and RPM for time. Now it's starting to come together for you. So all we have to do here is figure out, well, if we know that it's going to double for every 14.5 approximately, then we just need to figure out, well, how many bar are we going up here? And we can kind of do some similar math. So our estimated load, basically the first thing we need to do is create a multiplier. So equals the amount of boost you think you're going to have divided by 1 bar, which is about 14.5. Okay, so we're going to be running about 0.75 bar of pressure in this case. And of course, this is in addition to the 71.5 we have. So what we should be able to do now is take this number multiplied by that, and we have 54 load. So at 11 pounds of boost, what we're saying now is we should have about 54 more load than naturally aspirated. So now to get the final load calculation, we're actually saying now take this number that we've come up with plus the original naturally aspirated load, and that should be about the load we're hitting at this amount of boost. So wrap this whole thing in parentheses, order of operations, and then add to that the original 71.5, and we come up with that much load, and then we can just copy this now all the way down the table. And because we said no boost down here, we're not really concerned with it, I guess I should say. You notice these numbers all stayed the same as this. So that's about what we get up to. So this is really just for us to have a reference. So again, the big thing here is that this assumes that you've done this to figure out what your NA load was pretty accurately, and that you have some indication that's relatively close for boost. Now, again, with a blower car, the concept of overboost is generally not a thing. With a turbo, turbos can let go for all kinds of reasons and suddenly have big spikes. So you can usually keep the maximum load in your table a lot lower and more reasonable with what your estimates are than you can with a turbo car. Turbos, you probably want to have a sort of a safety net that if something does get out of whack and your boost creeps, you need to have something considerably higher than you think you're going to get. So 200 might always be a good idea to have in that top row on a turbo car, even if you don't think you're going to get there. And then just have a massive drop in timing on that top row. Have the next one down just slightly higher than what you should be getting. Okay, so now that we've estimated load based on this particular combo, we see that we should be peaking out about 147, so we'll call it 150. And I want to leave myself a little wiggle room because none of this is perfect. So I'm thinking what we can do is we scale this thing out to 160 for this blower car. So we now have figured out that our goal with our new load scaling is we're going to have 160 on top. Okay, that's the only thing we've decided yet. Now, this is what we're working with, and here's what I can tell you. This row right here is kind of useless. I mean, the only time you can actually even get to 5 load is if your car is still in gear and you're decelerating and completely off the gas. And so the higher RPMs you're at and at 0 throttle, the load will get really, really low. But that's the only way. If you're touching the throttle at all, you are not here. In fact, if you're even at idle, you're probably at 20. So you are pretty much guaranteed if you are touching the throttle at all, you're at 30 or above at all times. Now, the other thing I want you to look at, so now we have a hypothesis that what we might want to do is make the bottom row in this table 30, because again, idle spark is not controlled here. That's a different table, another discussion. So we're not worried about if this is too much timing for idle. That doesn't matter here. This is only for when we're driving. And so we have to consider, well, what happens? Because ultimately, if you do achieve less than 30 load, and this is the bottom row that we put in our table, like we talked about earlier, it can't go any lower. This is the lowest measurement we'll have, so it's just going to stay at this timing even if you go lower. So let's think about, is something going to blow up if we do that? So here, if we have 30 as the lowest it can go at 900 RPMs, well, it went down to 20. That's only 2 degrees. And keep in mind, guys, this is bone stock 5.0 with like stock E7 heads, super inefficient. They're cast iron. They don't like any timing. So, this is pretty conservative. And think about this concept too. All these timing numbers, in our first timing video, we talked about you got to set the car at base timing at 10 degrees with the spout out. That's what the factory did. That's what they assume. So all of these numbers here are actual timing numbers you should be achieving, assuming that you're at 10. And if you guys even know old school, like everybody would twist their distributor and go an extra 2 degrees or 4 degrees, or some guys would get crazy and go 6 or 8. And but a lot of guys ran extra 4 or 5 degrees over all these numbers just by turning the distributor, and they didn't blow anything up. I mean, I did it too when I was younger. If you just got a pretty stock NA combo, you just want to get a few more horsepower, put some 93 octane in it, twist the distributor, you get a little bit more power. So my point with saying all that is that technically the lowest we go below this is 2 degrees lower. I'm not concerned that we're up 2 degrees. I don't think we're going to blow anything up here. Okay, right here, do I think we're going to blow anything up? Well, this is actually a much bigger gap of 6 degrees, but the truth is we're going to go well past this load very quickly anyway. So I might bring this down like a degree, maybe 35 or 36, but I'm not super concerned there. 38 to 33, same thing. I might go down to like 36, or even just leave it at 38, not concerned. Small gap, 2 degrees, small gap, 2 degrees, small gap, 2 degrees, small gap. And in fact, this is where things start going up anyways. So this will even be less than what it would have been down here. And for other reasons that I'll get into later in the video, we're going to do some crazy manipulation here that gets way outside of what the factory did. So all that said, I think we're probably pretty safe to start at 30. So what I'm going to do is I'm going to copy that entire row. Since we've already scaled it for RPM, I can just drop it right in here. So 30 is going to be our starting point. Now, for drivability, what I like to do is try to keep all of these other middle rows above whatever I started with. So we're going to take 3 more rows and throw those numbers in. Okay, now we've got a few more that we can work with, and we have to decide what do we want to keep, what do we not want to keep. And this is the next important thing that I'm trying to decide. So now that we know about where we make our sort of max power naturally aspirated, we know what load that's going to be at. I want you to look at a commonality. This is a lot of where our performance is going to be right here, 3,000 to 5,000. This is a lot of that performance driving. These are all really, really close to 80 load based on actual measurements that we did with logging. So I'm very inclined to have a row in here that's set at 80 because I know if I do that, you know, it's a good jump off point to know what was the max timing I could take naturally aspirated. Now I have a good place to put that if I have a row at 80. So very inclined to put an 80 row in here. And the other thing I want to make sure, just making sure I got my counts right. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, just making sure. So now the question is, can I put 80 here and get enough out of it with the rest of this? Well, this is probably going to work okay. So if I've got 80 here, then what I could do is maybe kind of divide my way through here. We could go something like a 130 there and maybe a 110 here. So that'll give us a decent range. 160 is above what we think our max load is going to be, but it does give us a pretty good range to work with. And I know that a lot of these cells have a really good jump off point at 80. So this actually might be a pretty good starting point for our scaling. So 30, 40, 50, 60, 80, and then some somewhat even increments going up from there. So let's, again, nothing's perfect, but let's go with this. Let's say this is the scaling we want to have. And now we need to finalize this table. So right now we really have no idea what numbers we need to plug in here, but we're going to do something. It's not perfect, but we're going to do it. We're going to take all these numbers that we calculated based on the wide open throttle table, and I'm going to plug those in all the way up here because this is what a factory computer would have done. It doesn't care how much extra load you have. It would have frozen it here. I'm not saying this is what we're going to keep, but you know, that's basically the equivalent of just going up from where we were. So this is kind of what our table looks like now. And now the final task is to figure out how many total pounds of boost do we have in each one of these different cells, these higher loads at different RPMs, so that we can pull from this an amount of timing that we think is a 1-to-1. Every pound of boost we go up, we want to pull a degree. Go up a pound, pull a degree, and we can work from this. So what I'm going to do is I built a little cheater table right here because it makes writing the formula easier. That's the only reason. But again, these are the same RPMs that we're working with. And I want to write in what we've already calculated, all of these numbers here, which was the maximum load we're able to achieve at these RPMs all the way through the range. So I believe, actually, I'm going to try to pull this off. I think I can copy this, and then I can transpose this. And it reversed it. Okay. No, I was trying to be lazy. That didn't work. I'm not super good with Excel. I'm okay with Excel. So 68, 69, 70, 72.75, 75.25, 78, 82.25, 80.75, and 7150. Okay. So maximum load that we can achieve in A. So if I'm now trying to figure out approximately what load or what timing I want to have at all these different places, I need to figure out the boost. So what we know is this. We've now figured out approximately what load and what boost we're going to have, but now we need to figure it out at these different cells. So we can work from all these numbers. So at 6,000 RPMs, we think we're going to have 11 pounds of boost at 125. So that would be at approximately here. But again, we want to come up with a formula that allows us to do this. So I'm going to pause my brain for a second, pause the video, think this through, write a formula, be right back. Okay, recording resumed. So here's the formula that I've just worked out. So again, basically I'm saying I know what load we're trying to measure for this cell. I know what we did naturally aspirate. So the question is, how many pounds of boost do we have here? So what we need to do is first, we need to take the total load that we're working with here in the cell and divide it by what we had naturally aspirated. Okay. So basically what we're saying is we're 205% of whatever this number was. So that's approximately 1.05 bar above naturally aspirated. So now we have to subtract the 1, which would be the one we've already included here, to figure out what's the increase over stock. So take that number minus 1. So now we know that this is 1.05 bar, which if we multiply this by 14.5, which is PSI, that would give us the pounds of boost. So I should be able to take this entire number and multiply it by 14.5. And now we know that we are at 15.24 pounds of boost approximately in this cell. Now, for us to be able to copy this formula very quickly and just fill out the whole table, then there's something else we need to do here. So what I know is that as I copy down here, I want this exact cell to stay, whatever's in column or row 43. So if you put a little $sign right there, I can just keep copying that. And that should be the only change I need to make. So I should be able to copy this all the way down. Okay. So now we're saying at each load, so at 130 load at 3,000 RPMs, that would be about 9 pounds pressure. At 110, it would be about 6 pounds. At 80, it would be about here. So that's a pretty good area to work from. And then what I should be able to do is copy this all the way across the table. Unless I did something wrong, which I'm sure I did. Yeah, one more thing we got to do. And we want to make sure as we move left and right that we're not moving out of this 160. So what we need to do is we need to lock column 8 there, which would be a $sign. Okay. Sorry, guys. I'm doing this on the fly. So if I copy all that back in, my numbers stay the same, which is what I want. Now I should be able to copy this. There we go. Perfect. Okay, so now what we have at this point is we can see at each load in RPM, we know about how much boost we have. And I'm going to run the number of decimals down because this is pretty ugly to look at right now. Okay, that's a little easier to deal with. So of course, you know, when you're down here, you're in negative boost or vacuum essentially because you're not totally beaten up on the motor. So I actually am just going to erase all this stuff down here, because we don't need it. Well, actually, I'll leave it in, but it's not important. All we're really caring about is the cells where we are achieving boost, and then we need to plug those numbers in up here. So what we're saying is that looking at our final table here, we want this to be whatever we decided was acceptable naturally aspirated, which is essentially what this entire table already is, and subtract from that whatever these numbers are. So if that's what we decided here, and we subtract from that what we have here, we get timing. And again, we only need to do this for the areas when we're under boost. So like here, when we get down here, not something we need to mess with. So actually, I am going to do this because this will make these numbers jump out at us if we just paste the whole table in. This will be a little easier to work with. Okay, so those are wiped out. So everything else that we have here is usable. So paste that into the entire table. So what you notice is all these low rows, because these were essentially zeros or empty, then it's just the exact same value we had naturally aspirated. But when the boost does kick in, then we're starting to pull that down. And then the final thing we'd want to do here is we also want to do that same M round that we did earlier, because we can't put these numbers in. We need to round to 1/4 of a degree. So we change our formula by saying M round, that comma 0.25, and then we can copy that to the table. Okay, now you see a couple things jump out when we try to round these numbers, and it's essentially happening because we have so much boost at these low RPMs, which we're never even going to use this anyways, but we actually end up with these negative numbers down here. Because if we were only going to plan on 8 from the factory, and then we pull 20 from that, we're actually getting into like after top dead center timing. So what I would essentially do is anything that's gotten to that point, I would just zero all these out. You shouldn't be even getting into these cells anyways. I mean, you just shouldn't be all the way to the floor at 900 RPMs and just going crazy with it. So this is probably a pretty decent table to work with here. Now, some of these sort of mid-range cells right in here, you might need to put a little more timing in there, but for right now, this is a base map, trying not to blow anything up. This is probably about okay. Now, we're pretty close to having a final baseline table to work with, but the one thing we haven't really considered is, you know, the cylinder heads that we're using. Like, do we have a kind of a common aluminum head, something from, you know, Edelbrock or AFR, Trickflow? I can tell you pretty much any aluminum head will, not always, but almost all the time, take more timing and stuff. In my experience, like the AFRs will take a lot of timing compared to a factory head, like a lot more timing. Trickflows take quite a bit too. There's some others like Canfields and Brodix I've seen in some situations that don't like a whole lot. And of course, if you're still running anything cast iron, you know, GT40 heads, I've got some old cast iron RHS heads or like Pro Top lines. You know, those don't like a whole lot of timing. They don't dissipate the heat the same way aluminum does. So they hold on to it, and it's a little troubling sometimes if you try to really turn the timing up. So, but the one thing to consider is this is still all based off of generally stock setup, which assumes pretty inefficient heads. So what you may be able to do at this point is take all of these kind of higher end performance cells, you know, higher load, higher RPM, and probably increase this by some number of degrees of timing based on how much more efficient you think your heads are based on the MBT characteristics. I'm not going to tell you how much to increase it. And I also would tell you, don't increase it until after you've at least tried to run this first as it sits. And if everything goes okay, then you can start to pull things up from there. But, you know, this is really what you're working with. And what I want to show you now is I want to kind of go back to something that we talked about. So this is kind of all the safety net. Like, we're not actually planning to get into this high of boost at most of these places. So what I want to do now is go through an exercise where, based on what we think we're going to do with our setup and the amount of boost we're going to have, what of these cells are we really likely to be living in when we're at wide open throttle? So at 6,000 RPMs, we think we're going to be about 125 load. That's pretty close to this cell. It's actually somewhere between these two. So I'm going to go ahead and highlight these cells for a minute. Then I want to kind of point this out. At 5,000, we think we're going to be at about 147. So we're somewhere up between these two. At 4,000 RPMs, we're at 127. So we're almost spot on that one. So I'm just going to highlight that one. At 3,000, we're at 100. So we're kind of between these two. 2,500, we're at 85. So we're now getting pretty close to just living here. Okay, 2,000, we're at 77, so we're almost exactly right there. And at 1,500, then things kind of start to drop off where we're, you know, this doesn't really matter as much, but that's kind of what your actual curve looks like. So even though we have these higher numbers up here, it's very unlikely you're ever going to get into here if these estimates for boost and these other things we've done are pretty accurate. But what I want you to pay attention to, because this is really the entire essence of what we're trying to do. If we could tune directly based off boost, this would be so much easier. but we can't. We have to do it based on load, and load changes with efficiency of motor. So I want you just to think about something for a minute. If I just make a little dummy map starting at 2,500, 3,000, 4,000, 5,000, 6,000, without even getting into math at this point, because it technically doesn't matter. About what timing do we have? 21.5 degrees. Okay, here it'd be the average, and I know it's not actually the average, but this is just to demonstrate something here. The average of those two is about 19. At 4,000, we're about 14.75. Here, we're the average of these two. And here, we're the average of these two. And here's what I want you to notice. The boost keeps climbing, and guess what? Your timing keeps getting pulled. And then the boost went down a hair at 6,000, at least in this map. So then it went slightly back up. But this is the way you can have a very true curve based on the amount of boost you're running. If you just assume that, like, oh, once I hit 130, that's X pounds of boost all the way across, it's not. So if you try to lock your timing, and this is what a lot of guys try to do, let's just lock the timing at 18 or 20 or whatever you do. Well, that amount of load doesn't reflect the same amount of boost at different RPMs, and it's not the right way to do things. This is the right way to do things, in my opinion. It requires a lot more calculation and kind of going through this exercise, but it's actually not that hard once you grasp all the concepts we've just walked through. And this is what you need. What I'll probably do, if you guys want, send me some comments on this video, and I'd be more than happy to upload this spreadsheet, kind of clean it up a little bit so you have all these formulas, upload it so you can kind of work your way through it, put it on Google Drive or something. But this is really what you have to do. So now that we have all of this, one quick exercise is we're going to go change the scale, plug the numbers in, and then I'm going to make a quick follow-up video, just like we did with the RPM scaling, that once we do that to accommodate this sea-level table, we have to remember this load scaling affects a bunch of other stuff. So in the next quick video, I'll show you what else we'll have to change. So let's go ahead and get this thing locked in. So let's go into our scaling down here in system, and we are scaling Spark load rows. So we got to plug in our numbers here. So row 0 now is going to be 30. So I'm going to plug in 30 right there. Okay, and then we're going up in even increments, 30, 40, 50, 60. So the next number we need to put in here is 60. So 30 is 0, 40 is 1, 50 is 2, 60 would be 3. Okay, and then we jump to 80 at the next one, so that would be at position 4. And then we go 80 to 110, 110 to 130. So 80, 110, 130, 160, and 6, and 7. Okay, now let's go just double check our Spark table and make sure that I did that right and that it looks the way we expected. So putting these guys side by side, I think we're going to be all right. So 30, 40, 50, 60, 80, 110, 130, 160. Okay, so we've done that right. Now I'm just going to copy all of my values here, go over to binary editor, and paste in the whole table, and we have a starting point. Now, another quick thing I'll tell you guys is, with these lower boost combos, if you're under 10 pounds of boost, I find myself hovering around one very specific timing number a lot that seems very safe with, 91 or 93 pump gas. And that's around like 17, 18 degrees. So don't just do this, but, most combos, it's a pretty good starting point to target somewhere around there based on that amount of boost. And again, with the exercise we just went through, you could see that this is probably actually a hair conservative, but until you really know what you're logging, what you're doing, don't go blow stuff up. So that's kind of my tip for the day is, plan on maybe raising these numbers up once you can get some time, but need to kind of think this through. And if you figure out that something about this fundamentally was off in your initial estimations and you're going way higher in your load here, you definitely want to change your scaling here to accommodate something with higher load. But remember, you cannot put in numbers higher than 200. And if you find yourself in that position where you're actually pegging and hitting 200 and it's still trying to climb, but it can't, there will be another video for how you solve that. Again, more math. It's kind of not that hard, but it's hard until you know how to do it. So I'll get this one out right now, and then I'll probably have another follow-up video here shortly. Appreciate it, guys.